talking tonight, and
All right.
we should have a good time. So.
All right. Yeah. So I'm the guinea pig. Um, my name is Adam. I think this is the first public tech talk I've done. So I have my beer and be gentle. And yeah, it's a lovely slide, right? So I work for a company. Just to introduce myself a little bit more. I work for a company called Frontline Education. I am a remote employee here in Bend, and we do back office software basically for K through 12 schools, talent management, hiring, HR stuff, professional development for teachers, all that kind of stuff. So I have mostly worked there. I've worked there for about 2 years, mostly writing JavaScript for backend Node stuff. And I started taking a look, playing around with TypeScript about 6 months ago. And we shipped our first TypeScript to production about 4 months ago. And I think we have like 6 or 7 node services running TypeScript now in production. So we're taking it up and like it. And I also say that just to give a caveat, I'm definitely not an expert in TypeScript. So I've been using it heavily for about 4 months. But in figuring out what I wanted to put in this talk, I definitely learned some new things. So it's much for me to learn some things as you guys too. So. I think from our first meetup, I heard a lot of people who maybe wanted a TypeScript talk were coming from people who had no experience with the language at all. So this is very much an introductory talk. We're going to kind of go through some of the basic syntax on how the type checker, type annotations, how the type checker works. It'll mostly be in the editor, so I have some slides up here, but we'll just kind of hit the slides really quick and then flip over to the editor so you can see the syntax and what works and what doesn't. So what is TypeScript? So this is the really basic part. It is a superset of JavaScript with static typing. That's really its purpose, is to bring static typing to JavaScript. Since I think we have a pretty large, diverse group, does everybody know what static typing means? Does everybody need? Okay, so it looks like yes. All right, so that's really the main kind of thing with TypeScript. The language spec does include future JS features, dynamic imports, decorators, and stuff. There's nothing special about what TypeScript does there. If you want to transpile that stuff with Babel or whatever, it doesn't really matter. The interesting thing we're going to talk about is static typing. And compiles all that stuff to configurable targets. This is overlap stuff with things like Babel, so you can choose what ECMAScript version you want to compile to, like that. So kind of going back to the first point, since TypeScript is a superset of JavaScript, plain old JavaScript is valid TypeScript. So you can take a JavaScript file that you've already written, run the TypeScript type checker, and if you haven't done anything stupid, that's valid TypeScript. So I'm going to flip over, and we can just kind of see. Like our first very basic, to change my font size. Turn up the mic? Okay. Okay. It's a little better. We should also talk into the mic instead of face the screen. So, all right. So this is a TypeScript file, a TS extension, but it really looks just like JavaScript. We're just declaring a variable and setting its 5. I can compile this. The TypeScript command line tool is TSC. So I can run TSC. Returns without error means it's successfully compiled. It's set up right now to throw that into this build folder. And I can go look at the compiled file, and that's the wrong one. Because that would be crazy. So it didn't really do anything, right? Because it's not really doing anything. It's basically just spitting back out that JavaScript after checking types at compile time. So We can see like really quickly kind of what it brings if we try to do a couple things that aren't type safe. It knows that this is a number. It has TypeScript has type inference, so I can command hover over that, and you'll see there my number it's a number literal type 5, and we know we can't call split on a number. You know, if I declare a string, I know if I misspell stuff, it's going to yell at me and recommend stuff. So I can fix my my stupid mistakes, and it'll stop yelling at me and compile. So comment goes back out, so I'll code our compile later. So the big question is why? And this is really my experience over the last 4 or 5 months. There's probably some other reasons, but so I've enjoyed like that immediate feedback when writing code, when you're doing things that are not type safe, deep property access and stuff like that, where you might have nulls or undefineds down in objects, and you're trying to access stuff below that. There's a lot of immediate feedback that you get to catch in a statically typed language that you're not going to see in JavaScript until runtime. So the biggest thing for me are kind of these 2 next points. So in my largest TypeScript project, that type information that I've explicitly declared really is a communication tool, both to my teammates and to my future self. When I go back 2 months later and I have no idea why I wrote that code, those type annotations and how I've defined my shapes of objects communicates a lot of information to me, instead of having to do that through documentation or kind of implicitly trying to understand shapes of things and types in dynamic JavaScript. So discipline and design is probably both a pro and a con, but I found that it's really helped me think more about my API designs up front. What kind of objects I want functions to take, parameter order, all that stuff. So as I define my types, it's clear to me where I have common ground between different parts of my application and where I can reuse some of those type definitions. And in my experience so far, I think that's helped me design cleaner APIs for libraries and internal code. And last but not least, refactoring is way more better in a large application. Application-wide renames and code moving stuff. If your editor supports it, I use WebStorm. It works 1,000 times better than a JavaScript. Very rarely have to do the find text and replace and that kind of stuff. So you can refactor function signatures and all that stuff a lot easier and have a lot more confidence. So why not? There is definitely extra friction. Despite the fact that we just had like a really stupid little JavaScript file, TypeScript file that we compiled, for anything significant, there is more friction around setting up the toolchain. And it's definitely unnecessary overhead for proof of concepts, prototyping, small projects. If you're writing, a 50-line module, doing that overhead may not be the best fit. And certainly more syntax to learn, concepts to understand. If you're comfortable in dynamic JavaScript and dynamically typed JavaScript and don't want to pile on extra things in your head, you definitely have to learn some new things. So it's pretty easy to set up. All you really need is a tsconfig. Actually, so depending on your build chain, you may not need that. You might define your config in Webpack file or whatever. But basically, TypeScript takes a set of configuration options that describe what some of the options for the type checker, where to build the files, do you want to emit source maps, all that junk that we all love about setting up JavaScript projects, and a TypeScript file, and that's pretty much it. An empty object for your config will get you some initial defaults and start building TS files into JavaScript. So To actually look at what some of the syntax looks like, I'm not going to go through this on the slide. I'm going to drop it in the editor. Yeah. Yeah, so all these files and that a PDF export of that deck is on GitHub. So. Yep. Yep. So the basic types basically follow right along with JS since it's just a superset. The type inference is pretty simple for cases like this. You can see it'll. I don't know how well you can see that. It's kind of small, but the type checker knows that this is a Boolean because I've set it to true. I can also explicitly give it a type annotation, a Boolean. The basic syntax for type annotations in TypeScript is an identifier and then a colon and then a type. So you'll see that all over the place. And simple stuff like this, there's not a lot of value add to be explicitly giving type annotations. It's pretty clear what's going on. Sometimes people will give type annotations like this just as a communication tool, but numbers, strings, arrays. Again, we can infer that this is an array of numbers. A type annotation for an array, there's a couple ways to do it. The first way looks like this, where it's the type followed by square brackets. It can also infer mixed arrays. So we'll see the union operator later, but basically this is, it's inferred that it's an array of numbers or strings. We can figure that out. And then if I give explicit type annotations, again, these are kind of the two syntaxes, a type with brackets or an array keyword with a type variable that specifies the type that's going in the array. We'll talk about type variables later. You also get a tuple type, which is basically an array that's fixed length, and you can define the types in each position that's ordered. So basically an array of two numbers. That's it, an array of a number in the first position, a string in the second position, nulls and undefines also. There's a few other primitive types that we'll talk about a little bit later, but this is kind of like the basic set until you get into objects. So like we saw before, right, it's going to yell at me if I do stupid things like declare a variable, set it to a string, and then rebind it to a number. Or try to push a string onto an array that it's inferred as an array of numbers. And you can see this in TypeScript compiler. Yeah, WebStorm will yell at me, but there you go. That is something I was going to talk about. Yes, there's not runtime checking of the types. Everything's at compile time. There is a decent library I've used that actually has some runtime checking, and then so it allows you runtime verification, and then it'll actually emit out the TypeScript static types for you. So I have to find that. I can add that. But I don't remember the library of it. But by default, yeah, no runtime types. Yeah. Yeah, that's a good idea. Yeah, you probably can't see like the little squiggly red lines there and stuff. All right. You can also do inline object definitions. So this is a type annotation, just like number or string or whatever. That type annotation says it's going to be an object with a name property that's going to be a string. So that's valid. I can assign that. Just like our other errors, since it's going to be I need a string as a name. This one has a first name. It's going to tell me that object literal may only specify known properties, and first name does not exist in a type name string. So you can also define function signatures. pretty easily. It's a similar syntax, identifier for the parameters with the colon and the type, and then a return type that goes right after your parameter list. So this is a function add2 that would take a number and return a number. Yeah, that's stupid. Don't do that. It won't compile. This is also just a function signature function definition, not in the arrow function way, but in the older function keyword way. So taking a string, returning a string. Type literals work for numbers and strings. So you can narrow those two types down further and say that, for instance, this will actually infer that this inferred number literal variable, its type is 5. Its type is not number, it's just 5 because it's a constant. If I were to change this to a let, since I can rebind it now, I believe it'll now infer it as a number. You can also give type annotations for string or number literals. So very explicitly, this should only ever be 5. If I say it should be 6, it's going to give me an error. Works the same way for objects. Object literal. I want this object to only ever be named John. So that's basic type annotation and type inference. Interfaces. So interfaces are a way that we define, other than the type literals, we can define object shapes and the types of their members. And then we can also define function signatures, what kind of parameters and return types, and reuse these interface definitions throughout our application. So this is what an interface definition looks like. This is compile time only. So interfaces, it will not affect your compiled JavaScript. They don't actually, those type annotations don't get thrown into JS at all, since there's no runtime component. But you can export them, use them wherever, just like you would any other variable in JS. So interface, it's not always followed. Generally, a lot of people put it. It's kind of a convention of putting an I, like a lot of other languages will do I whatever for interface. So, but a person, first name, last name that are strings. This conforms. You use interface identifier just like you would any other type annotation. So that's me. And yeah, it will complain if I give a number for a first name. So function interfaces, you define a signature. Basically, that looks pretty similar, interface keyword, but you give your parameters in parens and then the return type. So this would be a function that takes two strings and returns a string. And I can declare a function, again, type annotation just like any other, that takes two strings and returns them concatenated with space. You'll see that since I've declared that it is I full name, that I don't have to annotate the parameters or the return. That's inferred by the fact I'm fulfilling that function. So yeah, it doesn't work because I'm passing in numbers. Type 1 is not assignable to a parameter of type string. We also have a facility for optional properties. That's annotated by a question mark before the colon. So middle name is now not required in a I many named person. So I can declare someone with just a first and a last name, but I can certainly add a middle name too and not be complained. Optional property. We also get read-only properties. So this gives you some of pseudo-immutability with objects. That's a read-only keyword before the key name. So we can see that here. It's going to complain. If I declare a read-only person with name Joe, I can't go back and change Joe's name to Jim. Because name is a constant or read-only property. We also get index signatures. Index signatures are a way for us to talk about the types of keys that we access dynamically with square bracket notation. So this interface is saying it's an object where a string key has a number value. It doesn't really care what the key is as long as it is a string. So I can declare an empty object with it and then with a variable, as long as it's a string key, access that. You can have number keys. So you can have different types for string keys and number keys. I don't really know why you would do that, but there's probably a use case. So I can say that if I have a number key, that I actually want the value to be a string. String is not. No, I can't. I'm not sure why I can't. Well, that's definitely something I don't know. I can tell that a number key should be a number, but I can't tell that a number key should be a string. That's referring to objects, yeah. The keys of the object. Oh, interesting. Why? I don't know why. That's true, you're right. Yep. We can also extend interfaces. So this is sort of an inheritance thing. I can say I now want a something that's a person with an age. I've previously declared this iPerson and go to that declaration. It takes a first name and a last name. I now want to say a person with an age also has an age. So I can extend that existing interface. You'll see, I'll talk about getting typings for existing libraries a little bit later, but this is, you'll see a lot of interfaces is based, how most of typings for libraries you'll use are implemented for function calls and the stuff they expose. So. Yeah.
So can you actually make an interface with like
Yes. Yeah, so I can say Drew, right? Yeah, okay, sweet. So your name is a string, but I can also have a function in there that takes, I don't know, takes an age, which is a number, and also returns a number. I can combine these also, so I can also have some crazy property that is an iPerson with an age. And I can have some other crazy property that it's an object literal that has a number in it. So anything on the right of those colons is just a type annotation. It can be any type of type annotation. It can be an arbitrary complex type annotation. So basically, if you have big crazy API shapes that are nested 5 deep, you'll see generally something like this, where an interface is defined for each resource type, and then you sort of build up interfaces to represent that shape. Okay, so type aliases. The next keyword we're going to introduce is the type keyword, and that just declares a type that can be used anywhere else, and you can declare a type alias with any type annotation. Just like in here with interfaces, we saw any of these properties can have any type annotation. So type aliases. Type age is a number. It's just a number. It's just giving me an identifier to refer to elsewhere as an age. I can export those just with interfaces and use them wherever I want. I can define object literal types, type aliases. So a person. This looks an awful lot like an interface. The question kind of being, if I'm defining object shapes, what's the difference between defining it as an interface and a type alias? And the answer is there's not a lot of difference. People do it both ways. Most of the community leans towards interfaces. They're a little bit easier with third-party typings to merge some of your own type information into libraries and stuff like that. So they're a little more flexible. That's a topic we won't really get into, but internal to your application, they are pretty functionally equivalent. Whether you use an interface or a type alias, there's a couple things you can do with type aliases that you can't do with interfaces, but like for instance, mapped types, which lets you do something like this. Read only. So this is actually type variable stuff, but you can basically map over the keys in a type literal and do things to them like this. Become read only. So this is just an example of something that conforms to that person that's now, well, it was read only, I guess, on each property. So. No, at least not that I know of in any easy way. So once you, they can be compatible. So one thing, so TypeScript is structurally typed. So meaning when it's figuring out whether, and when the type checker is figuring out whether an operation is going to be allowed, it looks at the structure of the type. It does not look at the identifier of the type. If you have a type person that has a name and an interface cat that has a name, it deems those compatible. And if you assign a person to a cat, it's going to allow it. Sure, you can. Yes. Yep. Yeah, so I think, at least the way I interpret your question, I don't think I can say I want an interface. Right. I've actually never tried that. And apparently it works, so I didn't know that. So yes, you can. Union and intersection types. So this is a mapped type. I don't really have any detail about map types, but basically what read-only is doing is mapping over all the properties in this object literal and applying a read-only annotation to them. So it is equivalent to doing this on each property. You can define your own map types. Read-only is a built-in one. Partial is a built-in one. So it you can say a partial person basically is making all of these properties optional. So this is how, like, if you know, you're a function like in Modash or whatever that is picking properties out of an object. Probably a type definition for that would be a partial of your input type. Union and intersection types. All right, so union types are ORs. Nullable number. It's a number or a null. It's a vertical bar. It's pretty straightforward. I can annotate these as nullable numbers, and I can set it to 5. I can set it to null. We're all good. You can union an arbitrary number of types, a string or a number of Boolean. It can also be some arbitrary whatever, read-only, whatever, it doesn't matter. You can use those in your interface definitions, type definitions, wherever. You'll see, you know, type or null a lot for like APIs that return nulls. Intersection types are ands, basically. So if you have two types, a type cat, your cat has a name, and something that's furry, has a fur color, you can have a furry cat. That's both a cat and furry. And your cat's name is Cuddles, and it has white fur. So that works. I think there are some nuances, but that works sort of like interface extension, in that you can kind of merge two type definitions. But that's more on the object literal side. Escape hatches. One type that we haven't seen is the any type. The any type is assignable to all other types. It's basically opting you out of the TypeScript type checker. It's basically saying this thing, in this case, foo, I can do whatever I want to it. It's assignable to any type. So it's an any. I can assign it a number, and now I can try to split it like it's a string. And the compiler will not complain to me. It will let me compile, and it will fail at runtime. So it's basically putting you in dynamic type mode. Start calling into it? So yes, so generally, if it can't infer anything out of that library, it's going to consider all those things, more or less. So here's just an example of a dictionary. You know, I want an object that has a bunch of keys and just whatever I want. It's any. So I mean, there's some valid uses. There's not a lot of if you see your code littered with any's, you're probably doing something wrong. Well, you're probably doing some things potentially that are unsafe anyway. Usually, if you feel the need for an any, it can be solved with type variables and generics, which we'll hit real quick. So type assertions are also another escape hatch, which is basically type casting for the type checker. So of course, a number I can't split. Gives me an error, but I can assert that that number is actually an any. These are equivalent. It's just two different syntaxes. You can do an identifier as annotation, or you can do an angle bracket in front of an identifier. I think in general the guidance has been to move to the as syntax. It's newer, and I think mostly because it's a little bit easier to read, especially with generics, when you end up with a lot of type variables. At least in my opinion, the angle bracket type assertions can get confusing with type variables. It does not. I don't think so. We can check real quick. Escape hatches JS. Oh, I got excluded. Yeah, it's just 5. I'm going to split it, so it's going to die in time. So here's another example. I can parse this JSON. I'm going to get back. It's actually not JSON. That's going to fail because I don't have the quotes in it. But anyway, I can I can assert that it's a number, and it's not going to be a number, and I can do unsafe things with it after that. So kind of like any, if you see your code has a lot of type assertions in it, there's probably a better way to express it. But occasionally, sometimes you know more about an object, especially if you're interacting with a library you don't control and don't have type definitions for. Is generally when you'll use it. But of course, the better approach is to write type definitions for that. Yeah, we can look at some too. So generics, type variables. So generics allow you to interact with objects and code in a type-safe way when you don't care about what type it is. Here's a really, so the basic syntax is on a function, you pass in a type, this is a type variable, t, in angle brackets before the parameter list. And I don't care, right? I'm just saying I'm gonna receive, there's some type that this function cares about. And I'm going to take an argument named arg, and it's going to be of type t. And this function is going to return type t. So the identity, it's an identity function. It's really simple, right? It just returns the argument. So I can call it with a string or an array or a number. I don't care. So a pretty classic example of where you might see a type definition that uses generics as an map function. So this is the built-in map function. I'm mapping over an array of numbers. Map doesn't care that it's numbers, right? Map just cares that it has an iterable that it can map over. And map doesn't care what type it's going to return. Map only cares that it's going to return something. So I can actually go and look at the type definition of map. And so this is unfortunate, but you'll see in the interface for an array, here's a type variable t. The t is the type of thing, primitive or object that's in the array. And then we also have another type variable u, which is going to be the return type of the mapping function. So you see that map, here's the mapping function. It's a callback function that takes that value t. So it takes that type that's in the array. It takes the array index that you're on, which is a number, and then the third is the actual array, so an array of type t, and it returns a u. Well, that function does, and then the whole thing returns an array of u's. So we're not explicitly giving these type variables in this function. TypeScript is inferring that argument is a number. It's inferring those type variables for us. Usually, this is how it works. You don't need to explicitly give type variables, but you can. You can also constrain your generics. So this is our type variable that we're going to pass in to this function definition where we want to print something's age. So we don't care what we get. We just care that we get a type that extends. This is a type annotation, this type annotation. It's an object literal type annotation that needs a key, age, and a number. This is our argument list. We're call our argument living thing. Because living things have ages, and it's a generic type. But we know we can, in a type-safe way, print this thing's age because we've constrained that argument by this a type variable constraint. So, no. Object literal may only specify known properties, and name does not exist in type age number. Super small. If you go look at like the type defs for a library like Lodash, they're super crazy and hard to understand, right? They operate across all kinds of different intervals, and they have, like they'll accept different types of arguments, depending on how you call it and everything. And it's super confusing. But so some examples that you actually see, like really, is promises are implemented as type variables. So a function that returns a promise, promise is a built-in type that, since it's built into the language, TypeScript already knows about it, and you give it the type that promise will resolve as its type parameter. And arrays, that's the alternative in syntax for array. So it's just a type variable. Enums. Enums are like basically the only thing in TypeScript, or one of the only things that actually produces runtime code. This is when you compile this, it's not just going to remove type annotations. It is actually going to write some JavaScript. It's pretty straightforward. First type of enums that have been around for a long time in TypeScript are numeric. Syntax is enum keyword, identifier, and then brackets with the key and value. I think you can omit the numbers, and I think it starts at 0. Maybe it starts at 1. I don't remember, but they'll count up. You can also just specify the first one. Count up. So I can say I want to start at 3, and blue's going to be 4. Sure. Oh. It's crazy looking. This should be one of the slides on the. I'm not sure. Say that again.
Yeah.
Yeah, there's a trick. So you can look that up. I can send a link out to. There's a good Git book, free Git book of TypeScript. I don't remember how he does it, but there's a pretty decent little trick to do that. Earlier this year, it also got string unions, so they work same way. They obviously won't auto increment. You have to actually give the strings for all the enum types. And enums really just become also like type annotations. So in an interface or a type definition, whatever, you can say county is going to be a county, and it's going to constrain that to the shoots or mult minima. It's basically the equivalent of a union type. So configuring, I mentioned the tsconfig JSON. Pass in command line. You can set it up whatever your toolchain is. But most of the stuff is very Googleable. Where do you want to build? What do you want your target to be? Do you want to emit source maps? Blah, blah, blah. There are two things that you would not know to look for unless someone tells you to look for or you run across them that are pretty important. I think are pretty important. The first is no implicit any. So, implicit any's. If TypeScript cannot infer the type of something, it will consider it an any. It's so small. So it's considering this argument an any. And it's not complaining about it. So likely what's happened is that we've forgotten to give a type annotation. This is so TypeScript allows implicit any by its default. My understanding is that that decision was made basically because it's a lot easier to convert existing JavaScript over to TypeScript. So when you turn on a type checker for your 100 files, right, it's going to light up. If it's going to throw errors when it runs across implicit any's, because that's probably a pretty common thing. TypeScript greenfield projects pretty much should have this turned on, at least in my opinion, most do. So I can turn that on. So here's my config. I can say no implicit. Implicit any is true, and I light up now. Parameter R implicitly has an any type, which is usually a mistake. If I really want it to be any, I can annotate it as an any, and my complaint goes away. So strict null checks is the next one. So by default, null and undefined are assignable to any other type. This means that if I annotate something as a number, by default I can set it to null, and I can set it to undefined. So that can introduce some pretty dangerous behavior because, whatever deep property access, right? I think that, something is going to be an object in this nested object, and I'm going to keep doing my dot chain and have confidence. Well, something's going to fail because something in there can actually be undefined. So strict null checks, whoops. Pretty much should be set to true unless you're converting over existing class. All right. So that's kind of the basic tour of the syntax. There's a lot of other interesting stuff going on in the language. This covers a pretty significant amount of stuff that you'll see in most projects. So interacting with third-party libraries, a brief question on that. Definitely Typed is a project and repository that can, so I should step back. So you can provide type definitions for any library by having an index.d.ts file and having your type definitions in there. TypeScript knows how to look for that, and it will pick up type definitions out of that. So there are an increasing number of libraries that expose their own type definitions. For libraries that don't, definitely typed is a repository of community contributed type definitions. So those are all namespaced in npm under types. So it's really simple to use. It really is as simple as npm install. I have yarn in here, so yarn add. So I'm going to do an Express project. I had that cache, so it's fast, but that's it. So I can now just import Express, and TypeScript knows to actually go look in that types folder for Express. I don't have to do anything. It's just it's basically me saying just pretend Express exported its own type definitions. It does. It just goes into my node modules folder. Yeah, so it'll look for the types prefaced. What did I have? Yeah. So there's a types folder now in my node modules folder. And installing Types Express got me body parser Express, basically all the stuff that ships with Express. So just to show a really simple, and I mean really simple API example using Express. So you can see here, I import Express like I normally would. I also import, these are type definitions that I just got from that type/Express. So these are not actual Express things. These are like an interface declaration that I can go and look, and I can see how, what the type definition for an Express request looks like. So in this case, it's just something that extends core request, which extends, this is a built-in, I think this is the built-in node request object. You'll see here, we didn't talk about this, but you can extend multiple interfaces. So and then here's all the things that it's adding to the default, the node request. So now when we have something, a handler, a controller, which this is, we can strongly type our parameters. The request is, well, I should step back, right? This is just showing, so you probably wouldn't do it this way, but I can extend that myself. So this is the Express request, and I know I'm going to pass this thing a query parameter. It's going to have a first name and a last name, and this is more explicit than what I would get out of the base definition, right? If I look in here and I say request.query and go look at the type def, the Express type defs just tell me it can be anything. But I know I'm going to get a first name and last name, and at runtime I'm going to validate it. Probably wouldn't do it this way, whatever. And now I know when I hit my controller, I don't just have an Express request, I have a name request. So I can look at rec query first name, and my type checker knows it's a string, and I can do stringy things with it. And when I said simple, I meant simple, because that's it. So That is it. That's TypeScript 101. So I should say, I don't, a couple things I forgot to mention.